Okay, I make us 2 minutes over, so you get added 2 minutes on your 20. Daan Crommelin will be talking about model uncertainty in turbulent fluid dynamics.
Okay, thank you. Good afternoon, everyone. It's a pity I wasn't able to make it actually to the UK, but well, that's how it is these days. I guess it underlines the relevance of the topic for the meeting. So what I'm going to talk about is uncertainty in the context of turbulent fluid dynamics, that including geophysical fluid dynamics, so atmosphere and ocean, which is something that I've looked at on a number of studies. So here, I wasn't completely sure what audience to prepare for it. So for some of you, this may be very trivial because you've worked on fluid dynamics yourself, but for others, this may be less familiar material. So let's take a brief look at so what is a challenge, or at least one major challenge when you try to simulate fluid dynamics, and that is that for nearly all flow configurations and practical turbulent flows, it is not possible by any stretch to resolve all the details of the fluid flow in numerical simulations, because it's just computationally way too expensive. And here on the right, you see a snapshot from a simulation. What you see is vorticity. It's related to fluid velocity. And what you see, of course, is a lot of sort of small detail, so sort of large scale features, a lot of small scale detail that is for which you need pretty fine resolution to see it and to resolve it. So what needs to be done if you want to simulate fluid flow? You need to discretize the partial differential equation that describes fluid flow. That's an Navier-Stokes equation, or in some say special or filtered version of it. And once you discretize, it can be done by various methods from let's say the toolbox of scientific computing. But for all these methods, there's some form of grid resolution that comes into play, and that means that there are all kinds of processes that are taking place at spatial scales that are too small to be resolved once you pick your discretization parameter, for instance, the grid spacing, if that's the type of discretization that you use. Right, so we have to deal with unresolved processes. They're not explicitly simulated anymore, and their effects on the behavior, the dynamics of the resolved scale, so the larger scale flow, needs to be represented one way or another. And that happens through the representation are typically called closures, or depending a little bit on the field or subfields, are also referred to as sometimes parameterizations, that more in the atmosphere ocean domain. Turbulence model, so it goes by various names. To see why this is complicated, to formulate closures and parameterizations. So here is in sort of this very simple, almost sketchy representation of a PDE for incompressible fluid flows. There is the velocity u, which is dependent on space x, right? It will be 2 or 3 dimensional, and time, and right, the time derivative. Let me see if I can draw the hand pointer. I hope you see it all on your screen. The mouse pointer. So there's the time derivative. This is the what's called the advection term, or sometimes convection term. So it's that's due to the fact of that the flow advects, and that is something that of course that affects the dynamics of the velocity field at a particular point. And there's forcing and dissipation, and I've not specified the form for that, but let's just leave it at these general forms of force distributive fluid flow. Now, what you can think of is decomposing this velocity field into a larger scale, or into larger scales and smaller scales. So the U bar denoting the field with, say, the larger spatial scales still resolved, and everything that sort of falls out is then the U prime field. And on the right, I've shown what that could look like in a very simple way of making this decomposition here for the vorticity field that I showed on the previous slides. Right, so on the so here's the full field, and at the top, and then at the bottom on the left, you see the sort of, looks a little bit as if it's blurry, as if you should put in your glasses or something, but it's really it's a large scale flow field, and then everything that's all the small details that are left out compared to the full field are here. Okay, now you can unearth all kinds of technical conditions that I'm not going to discuss here, but if you write down the partial differential equations for the large scale flow field, it's almost the same as the original one, right? So it's shown here. So again, we have the time derivative, we have the advection term here. Now in terms of U bar instead of U, there's forcing and dissipation, which also needs to be sort of force grained or projected onto large scale patterns. So that's all pretty much the same, but there's this new term B, which is causing all kinds of trouble. And that's what's often referred to as the subgrid scale stress term. And it is due precisely to the fact that if you do your, say, sort of filtering, projecting on large scale patterns of this advection term here, that is different from expressing that solely in terms of the large scale field U bar, right? And this difference is the SGS term, and that means that if you look at it, you cannot exactly express this in terms of U bar only, and that means that the PDE that we have here for large scales is unclosed, right? It's not a closed system, because somehow this term here needs to be, we need to infer it somehow. We need to come up with it or model it. So what needs to be done, and that is the idea of a closure, is to express B as well as we can in terms of the U bar field. Right? So this is the origin. I mean, it comes in there are some variations on this, but essentially this is the origin of closure terms. This is why we need to do this. Right, so it's a non-linearity of in the advection term of the Navier-Stokes equation. Okay, so this is simulating fluid flow. Now, if we go to more generally to the topic of uncertainties, when you model and simulate fluid flow, and I guess all kinds of other systems, there are uncertainties and errors and choices to be made. And I've listed some of the main ones here. Maybe you've seen a list like this already in one of the earliest talks, which I had to miss, unfortunately. So sources of uncertainties here, there are physical parameters that are not always very well known. There are initial conditions and boundary conditions for fluid flow that can be uncertain. On top of that, there may be uncertainty about the structure of the model, right? So the functional form of the model. And for instance, in the context again of fluid dynamics, I mean, there can be different filtered versions of the Navier-Stokes equation that you consider, where one is maybe easier to handle numerically than the other. But then, of course, that's right. If you go then for that simpler form, of course, that's maybe an error that you make, right? And the effect of that can be quite uncertain. And then finally, there are all kinds of choices that you're faced with when practically simulating fluid flows. Choices what numerical scheme to use, or schemes, for instance, for numerical discretization, spatial discretization, for time stepping, Related to that are choices of simulation parameters like the time step, if you use running time, the grid spacing, and so on. And then finally, there's a range of closures or parameterizations that have been developed and that you can choose from. And of course, which one to choose is not always obvious. And of course, that relates to the remark above about the model form uncertainty. So what closure to pick? Is it the right form? Is there still uncertainty there? These are of course related questions. Okay, now in computational fluid dynamics, uncertainty quantification is a topic that people have pursued already for some time. There's quite some literature on that. I've listed here two. One paper, a review paper, my Nudging from over 10 years ago, and another one, a book by Lemaitre and Knio from also over 10 years ago. So these give something of an overview, at least, of what was already done by then, of UQ methods in CFD, in computational fluid dynamics. I would say that from the method review there's a lot of emphasis on parameter uncertainty and uncertainties in initial conditions and boundary conditions. By contrast, model uncertainty is less explored, and I'd say is also more challenging still to tackle and to analyze. And what I want to do in the rest of my talk is go over a couple of ideas, some of which I've worked on myself and others not, how model uncertainty can be, well, I wouldn't say dealt with, but at least the ways to perhaps get something of a handle on this problem. So one thing is relating to this, what I mentioned before about this point, you have to make choices, right? So model choices. And this is from a study that we did in my group in Amsterdam about simulation with an atmospheric large eddy simulation model. And there are certain choices or switches that you have to make between the choice of the cloud microphysics scheme. Right? There are two different schemes for the particular alias model. Right? So it's a numerical model called the Dales model, and it comes with several choices for the cloud microphysics scheme. It also comes with multiple choices for the advection scheme. Right? So it's the numerical scheme for the advection term in that is in the model, and then. Besides that, there's a rain advection scheme, which can be treated a bit differently. There are three choices there. So how to choose that, and in particular, how to assess what the effect of those choices are. So what we did here was a fairly simple idea, but I wanted to show it nonetheless. We considered these model switches as, say, a discrete parameter, right? Choices for a discrete parameter, right? So it's on or off, or third choice, and we put uniform probability distributions, so discrete distributions over these various choices, and that's in that way sort of sample all these different combinations in order to explore the effects and the variance in the output of the model due to these different choices. And so I'm not going to discuss that in much detail here, but there's also, for instance, the choice of the tolerance of the Poisson solver that is part of the model. And there's also something you can choose, and in principle, you know that's in this case, right? The lower tolerance, the better the solution. In principle, it's also more expensive, computationally more expensive. So where to put it concretely can be difficult to decide on, because, well, where is the optimal compromise? That is not obvious a priori. Okay, so on this sort of a shortened figure from that, where you see, for instance, that's encircled in green, that's the cloud cover, which is one of the outputs of the model. The cloud cover is sensitive, as you see here, to the choice of the infection scheme, but not, for instance, to the choice of the cloud microphysics scheme. Right? So this was one of the somewhat unexpected outcome, at least for me, from this study. Okay, let me move on in the interest of time. So I guess a more systematic approach to compare these, right, to get a handle on these different choices between different closures or parameterizations or numerical schemes is to adopt the framework of Bayesian model averaging. And this has been done not by myself, but it has been done in the context of fluid dynamics, actually by my colleague Wouter Edeling, who already presented here. So you see figure here from his paper showing the probabilities of different models under different scenarios. And in this paper, they extended the Bayesian model averaging setup to also include different scenarios for different flow configurations. And the figure here shows that under these different flow configurations, there's not one model that always comes out top. It is really scenario dependent here. Okay, now a rather different line of thinking to explore or represent model uncertainties by stochastic modeling. There's inherent uncertainty of how resolved and unresolved processes interact with each other. And that is something you can try to represent with a stochastic process. Right? So in principle, time correlated stochastic process. And this, in particular, in the weather climate modeling community, at least or part of that community, has pursued this already for quite some time. In fact, Tim Palmer was one of the earliest to propose this and has pushed for this for a long time. So here's a very early paper of his on this topic, and this overview paper from Werner et al. is more recent and gives something of an overview of various ideas from a couple of years ago. Now,
about 2 minutes left.
I have only about 2 minutes left. So I had a couple of slides to show a little bit of why there is some theoretical underpinning for the idea of stochastic modeling, and that is if you think of model reduction in the context of the what's called the Moritz-Franzig formalism, which is the formalism to reduce models and come up with an exact effective model for that. And what you see here, so let's assume that we have coupled, so I'm doing this now in the context of ordinary differential equations. We have coupled ODEs for two sets of degrees of freedom, X and Y. Mostly interested in X and not so much in Y, then this we can do, well, at least formally, there's this effective model that I show here for X itself, and what it includes is not only typically modified deterministic part here, but also a memory kernel. There's a memory term and what is typically interpreted as a noise term. Right? So this follows from the Moritz-Franzig formalism, and not only, so I want to emphasize that, not only does it bring about noise, right? So it's a stochastic effective model generically, but it's also non-Markovian, right? Due to this memory term here. Okay, I had a slide here to show this for a simple linear system. Let me skip that. Right, so again, this the effective model. So that's, I'm just reiterating this point. The error that you make by leaving out certain degrees of freedom, for instance, all the small scale degrees of freedom, by that you'll make an error that includes memory and as well as randomness. To really carry out this model reduction is typically just too difficult, right? It's not feasible to really do this, say, analytically. So what has become popular in the last few years is to learn instead closures or pentorizations with memory, right? So inspired by this more responsive formalism from data, right? Using, for instance, modern machine learning technology. So two recent papers that are doing that are here by Pan and Duraisamy from a few years ago, and another one by a group of Jan Hesthaven. And the last few minutes, if I still have them, I was going to spend on some recent work that I did with Wouter Edeling, where we essentially also pursue this idea of learning a parameterization from data with memory, and it also relies actually on neural networks in a particular way. And the key idea is here is that if you want to iterate this model here, right? So it's a very sort of abbreviated way of representing the model. So there's a part that we know, right? So it's this capital F, so it's given to us, for instance, by physics, by discretizing a known PDE. But there's a part that we don't know, it's this R here, and the idea to represent that is to evolve that over time is to sample it from this conditional probability distribution. Right? So where we take the history of both this discrepancy, if you will, or model error, the history of it, and also of the model state itself into account. Okay, how that's done in practice, this is only a very brief slide on that, so let me skip that. I refer you to the paper for it, just show this last slide some results from that. So we tested this on a much used test model, considering coupled ODEs that are sort of somewhat representative of the, like in a sketchy way, of the dynamics of atmospheric flow, and it's the Lorentz 96 model. And we focus here on how well we do on reproducing long-term statistics. And what you see here on the left and on the right is that the length of the memory matters here. So it's a relatively short memory that we took into account here. So there's not a very good reproduction of our reduced model. That's the blue line with the original, the fully resolved model, which are the black crosses. If we extend that memory, then here we get a much better coverage of the statistics. Right? So this is, as I said, it's the Lorentz 96 model, but it's under parameter settings that are sort of non-standard, and they make it a very challenging test case. Okay, so just to, I don't really have a conclusion slide here, but I'm going to stop and just reiterate here that this whole idea of the more responsive formalism points to accounting for model uncertainty that involves, right, both non-Markovianity and noise, and that is what I wanted to show here. So let me stop here and take questions if there are any. Thanks.
Thank you very much. We thank our speaker, please. We're kind of a bit out of time, but while Peter gets mic'd up, maybe just chance for one. There is a question. No, anything online? Okay, so just one from me then. Given that in reality we only kind of get one realization of a model, how do you know that you're capturing all of the uncertainty within your turbulent structure?
Well, so I think for the kind of setup that I discussed here, the idea is to be able to do multiple simulations on a limited space and time domain, right? So you can do highly resolved simulations over, of course, over a limited time span, also over the limited spatial domain, and then take the data from that and use that as being representative for, of course, for one particular spatial domain, but then to use replicas of that, if you will, over the rest of the of your spatial domain, right? And your sort of extended period of time. That's the idea here. Right? So if there is, or of course that supposes that there's not something that is very strongly non-stationary in this sort of high resolution limited domain model going on. Because if that were the case, then of course this would be much more difficult to do.
Great. Thank you very much. Thank our speaker again, and hopefully you can come back for the discussion.
Sure. Thank you.
Thank you. So our next